So this is our first lecture on NMR, Nuclear Magnetic Resonance Spectroscopy. In the first session, we'll discuss some of the basic ideas on NMR. Then we'll discuss about the applications of NMR in organic as well as in inorganic chemistry as we go along. Right, the first and foremost important point, the very first point that you should keep in mind is NMR is a non-invasive. It does not consume the sample and it is non-destructive. Right, the molecule or the compound that you keep in the NMR instrument, after taking the spectrum, all the molecules in the compound remains as such. It is non-destructive. Molecule does not decompose. Okay, the molecule remains as such. So it is non-destructive, and the compound that you keep, right, the entire sample remains as such. It does not consume the sample. Right? So NMR is a non-invasive and non-destructive technique. Okay? So this is NMR is used to study molecules in solution as well as in solid state. Okay, NMR is used to study molecules in solution state and solid state. So you can study the compound in solution state as well as in solid state. This is another important advantage of NMR. Okay, NMR provides information about the nuclear properties of an atom or atoms of an atom, okay, present in a molecule, okay, or atoms present in of an atom or atoms present in a molecule, okay, present in a molecule or a sample. Right? So NMR, many scientists were involved in the development of discovery and the development of the NMR techniques. Okay. Number one, listen. Nucleus of an atom possesses a property called nuclear magnetic moment. Okay, we represent this shortly as mu(n). What is mu(n)? Nuclear magnetic moment. Okay, we are going to discuss this, okay, in a detailed manner, but right now I'll just introduce you the term. Okay, mu(n) means nuclear magnetic moment. Scientists Stern and Gerlach, they carried out an experiment. It's called Stern-Gerlach experiment. Based on this experiment, okay, right, based on the experiment, they discovered that nucleus possesses a magnetic moment called nuclear magnetic moment. And because of this work, right, Stern and Gerlach received the Nobel Prize in 1943. They received the Nobel Prize in 1943 for this work. Okay, for the determination of nuclear magnetic moment. Then number two, the molecular beam experiment was carried out by Rabi to study NMR in gas phase. Okay, NMR in gas phase using molecular beam experiments. Molecular beam experiment. This was carried out by scientist Rabi, and he received the Nobel Prize in 1944. Right? Then, you know very well, two groups of peoples, Felix Bloch and Edward Purcell. Okay, Purcell and Bloch. They studied the NMR. Actually, Felix Bloch studied NMR in water, and Edward Purcell studied NMR in paraffin wax, and they received the Nobel Prize in 1952. Right? Then other scientist, Ernst, right? He received the Nobel Prize. Okay, and a chemical shift was discovered, and so many things happened. Okay, and many people got Nobel Prize, and many people contributed a lot in NMR techniques and in the application of NMR in different areas of science. Okay, see, we'll discuss about the nuclear spin. Right? This is our next goal. What is nuclear spin? Listen, every atom in the periodic table, right, has a nucleus. Okay, you know very well, a nucleus carry a positive charge. Okay, this is a nucleus. Nucleus carry a positive charge. Carry positive charge, not a positive charge. Right? And you know very well, nucleus is made up of two fundamental particles, subatomic particles. Right? Other particles also there, but the two fundamental particles of nucleus are neutrons and protons. Okay? Right? So, and these particles are collectively called as nucleons. Protons and neutrons are collectively called as nucleons. So every atom has a nucleus, and the nucleus is made up of neutrons and protons. And you know very well, the fundamental particles, proton carry a positive charge. Okay, and neutron is a neutral particle, right? So let me write here. Proton carry a positive charge plus E. Okay, and neutron is a neutral particle, does not carry any charge. And just for comparison, I'll give this also. Electron, it carry a charge minus E, which is the magnitude is exactly same as that of proton, but opposite sign. Okay, these particles are called fundamental subatomic particles of an atom. Okay, then these particles have spin. Okay, it was studied by scientists, and they have given the spin angular momentum for all these particles. Okay, spin angular momentum for these particles. They have given spin angular momentum. Okay, for proton it is actually half times h cross. For neutron, half times h cross. and for electron of MH class. These are the spin angular momentum values of a proton, of a neutron, of an electron. Okay, this is for one proton. One proton has this spin angular momentum. One neutron has this spin. So keep this in mind. Even particle without charge has spin. Okay. Now listen. Since protons and neutrons have spin, why they have spin? We'll discuss. Right. So the nucleus may also have spin depending upon how many protons and how many neutrons are present. Okay. So individual proton, individual neutron, they have the property called spin. Okay, now a nucleus may contain one or more protons. A nucleus may contain one or more neutrons. Okay, now will the nucleus spin? Right? Will the nucleus of an atom spin? Do all the nuclei of atoms, right, have the property of spin? Okay, so this is actually a very important question. Because every atom has nucleus, but do all the nuclei spin? Do all the nuclei, right, nuclei spin? Let me ask a question like this, a simple question. Right? Every atom in the periodic table has a specific nucleus. Do all the nuclei spin? Observe carefully. The spin of a nucleus is decided by, okay, what is called the spin quantum number. Okay, spin quantum number I. What is spin quantum number? We'll discuss. Listen. If a nucleus has non-zero nuclear spin quantum number, nuclear spin quantum number, which we represent by the symbol I. If a nucleus has non-zero nuclear spin quantum number I, then the nucleus spin about its own axis. About its own axis. Observe this very, very important part. If a nucleus has non-zero nuclear spin quantum number, then the nucleus spins about its own axis. Listen carefully. What is this spin quantum number? Listen carefully. Every nucleus, right, has a characteristic value. Value of I. What is I? I is called spin quantum number. Every nucleus has a characteristic value of I. Right? If I is equal to 0, then that nucleus does not spin. Okay? So, if I is equal to 0, then that nucleus does not spin. Okay? If I not equal to 0, okay, what is meant by that? I may have value half integers 1 by 2, 3 by 2, 5 by 2, etc. I may have integer values 1, 2, 3, 4, etc. Okay, if I value is not equal to 0, then the nucleus spins about its own axis. Then that nucleus spins about its own axis. Listen. What is actually a spin? What is meant by spin? Listen carefully. Often in many lectures, right, people say that a nucleus is there, the nucleus is spinning in clockwise, or the nucleus is spinning in anti-clockwise. Okay, like that people are usually, right, in many lectures, right, you might have seen this. In many lectures, people say that nucleus spins in clockwise or anti-clockwise, right? Actually, if you represent the spin like this, okay, then it becomes a classical one. Okay, spin is purely a quantum mechanical concept. Spin, okay, is a quantum mechanical aspect, quantum mechanical concept, I can say, right? It's a quantum mechanical concept. It does not, see, this is very important, it does not have any classical analog. What is meant by that? You cannot represent spins like this. Spin is a quantum mechanical concept. It's a quantum mechanical property, I can say. Concept or property. It's completely quantum mechanical property. Right? Showing spin in clockwise or like this, if you show, then it becomes classical. Actually speaking, since spin does not have any classical analog. But we use this type of notations because, okay, it is easy to understand, right, the idea of NMR using these toy models. Okay, but actually speaking, quantum spin, right, spin is no way connected with these demonstrations, with these toy-like pictures. Okay, spin is entirely different one. It is a quantum mechanical concept. But we use these because the understanding is easier. Okay, anyone can easily understand the idea of the basics of NMR if we use this type of pictures. Okay. Now we'll discuss about I value. Okay. First, I'll give you what is called the empirical rule. Okay, using which you can say that under what condition we get I value 0, under what condition we get I value not equal to 0. Okay, that we can easily understand. Right? It's called empirical rule. Right? What is the empirical rule? Let me write here. Number 1. Rule number 1. Listen, if number of proton and number of neutrons present in a nucleus, if both are even, see, listen, number of protons present in a nucleus and number of neutrons, right, observe carefully, right, number of protons and number of neutrons present in a nucleus, right, neutrons, if both are even number, this is even, this is also even, if both are even, then that nucleus has I equal to 0. Okay, if both are even, then the nucleus has I value equal to 0. Right? If I is 0, you know very well that nucleus does not spin. Okay? The nucleus does not spin. Right? Examples are, see, suppose I'll take helium, He2O4. Helium nucleus. Listen, if I write like this, keep this in mind. We are talking about the nucleus of helium, not the helium atom. Observe carefully, right? Observe carefully. If I write like this, it means that we are talking about the nucleus of the helium atom, not the helium atom, nucleus. So helium atom nucleus has 2 protons and the mass number is 4. So 4 minus 2 will give you 2, that is called 2 neutron. So helium atom has 2 proton and 2 neutron. So proton number is even and the neutron number also even. Therefore I is equal to 0 for helium. He2 4. This isotope, observe carefully, this isotope has I equal to 0. Second one, C612, carbon 12 isotope. Here it has 6 proton, 12 minus 6 will give 6, so it has 6 neutron, both are even number, so I value equal to 0 for this nucleus. Right? Like this we have many, O816, 8 protons, 8 neutrons, I equal to 0, right? So like that we have many examples. So these species, right, the nuclei of these species, these atoms, right, they do not have the property of spin because the nucleus of these atoms have I equal to 0. Point number 2. This is actually rule number 2. If the number of protons, see, number of protons plus number of neutrons, observe carefully, If number of protons plus number of neutrons, if this sum, if it is an odd number, suppose if it is odd, observe carefully. I am adding the number of protons and number of neutrons in a nucleus. If I get the sum as odd, then those nucleus have half integer spin value. I is equal to half integer. They have half integer spin quantum number. Half integer spin quantum number. What is the half integer? 1 by 2, 3 by 2, 5 by 2, etc. Okay? Number of protons, number of neutrons. If you add the two, if the sum is odd number, then that nucleus has I value half integer. If I value is half integer, then the nucleus will spin. Okay. Examples for this type of nucleus is that the number of protons and number of neutrons, sum should be an odd number. Okay. So let me give you examples here. See, H11, then C613. Listen, the hydrogen atom has 1 proton. Mass number is 1. So 1 minus 1 is 0. So there is no neutron. And second case, it has 6 proton, even number. Right? But 13 minus 6 will give 7. It is an odd number. So 6 plus 7 will give odd number. Okay, just see the mass number, simple. Right? Mass number is odd, which means sum of proton plus neutron equal to an odd number. Okay, so C613, we have actually plenty of examples. N715, right, etc., etc. Right, the nucleus of these, right, nuclei of these atoms, okay, they have I is equal to half integer value. Okay, and these nucleus have this property of spin. Okay, they spin. These nucleus spin. They spin. Right? Rule number 3 here. If the number of proton, if it is an odd number, if number of proton is odd number, similarly, number of neutron also odd number. If both are odd, number of proton is an odd number, number of neutron also odd number for a given nucleus. In this case, right, we get I value as integer values. I value is an integer. Okay, integer means I takes values like 1, 2, 3, etc. Right? Yes, these nucleus also have the property of spin. Right? These nuclei also spin because I is not 0. Okay, take it. Examples are, let me write here also, N714. See, number of protons 7. 14 minus 7 is 7. Number of neutron also 7. Okay, so 7 proton, 7 neutron, both are odd number. So N714 has I value, integer values. Okay, N714. Then deuterium atom, okay, let me write here, nucleus of deuterium, H12, nucleus of deuterium, it has 1 proton, 2 minus 1 is 1, 1 neutron, so both are odd number. Okay, so deuterium has integer spin value, spin quantum number value or simply spin value. Right? So there is another way by which we can find the value of I. This is called the nuclear shell model. Nuclear shell model. Based on this also we can find the value of I. But this method also, this nuclear shell model also has some limitations. Okay, we'll discuss that. Now listen carefully. Listen, in the case of atoms, right, we arrange the electrons in different subshells. 1s, 2s, 2p, right, 3s, 3p, 3d. These are called subshells. So we arrange the subshells in the increasing order of energy. Then we fill each subshell with the electrons. Right, in a similar manner. Inside the nucleus, okay, we have neutrons, we also have protons. The neutrons are arranged in subshells called nuclear subshells. First, arrange the nuclear subshells in the increasing order of energy. Then fill each nuclear subshells with the available number of protons or neutrons. Okay, you have to arrange the neutrons separately and protons separately, like we arrange electrons in subshells. Right? Listen, like electrons, what I am trying to say, like electrons, okay, neutrons present in a nucleus, right, can be arranged in nuclear subshells. Okay, in nuclear subshells, and observe carefully, are arranged in nuclear subshells, and the nuclear subshells are arranged in the increasing order of energy. Okay, the neutrons are placed in nuclear subshells, and the nuclear subshells are arranged in the increasing order of energy. Okay, let me write here. Nuclear subshells are arranged in the increasing order of energy. Similarly, protons, right? Protons present in the nucleus are also arranged in the nuclear subshells. Okay, now listen carefully. What is the difference between electron subshells and nuclear subshells? There is nucleon subshell. Okay, I'll just use a common term. Okay, for neutrons and protons, right? What are the subshells, nuclear subshells available? Let me write here 1s, then we have 1p, 1d, then 1f, then 1g. Observe carefully, this is not the energy order. Okay, like that it goes. Then 2s will come after 1d actually. So let me start here. 2s, then we get 2p, 2s, 2p, then 2d, then 2f, like that it goes. Okay, then we have 3s, right? 3s starts from here after 2D, 3s, then 3p, then 3d, like that it goes. Carefully, here I have given how the subshells, right? What are the subshells available, right? Now I am going to show you how these subshells are arranged in the increasing order of energy, right? Yes, without LS coupling and with LS coupling, I will show both. Let me write the next page. Listen carefully. First, I will write without LS coupling, okay? That is orbital motion and spin motion. Listen, as the nucleus spin, every nucleon, right, moves around the own axis, moves around the nuclear axis, right? It is called the orbital motion. Not only that, every nucleon also spin about its own axis inside the nucleus. So every nucleon, it has orbital motion as well as spin motion. So LS coupling schemes also there for nucleons. Like electrons, LS coupling scheme is also there for nucleons. Now listen carefully. How the energies, right, of these subshells are arranged. Let me show you here. Just a schematic picture. So this is the energy order. Energy increases in this way, right? I'll give you how the different subshells, right, are arranged in the increasing order of energy, right? So first subshell is actually 1s subshell. So let me draw a line here. This line indicates it is a 1s subshell. I am just giving you without LS coupling, without LS, okay, right? Or I can say this is L value, based on L value. For S subshell, L value is 0, right? After 1s, we have 1p. 1p subshell. After 1p, we have 1d. 1d, then immediately we have 2s. 2s will come next to 1d. Okay, 1s, 1p, 1d. Then after 1d, we have 1f. 1f. After 1f, we have 2p. 2p. Then after 2p, we have 1g. After 1g, we have 2d. Then we have 3s. Like that it goes. Okay. So these are all this is the arrangement of nuclear subshells, right, in the increasing order of energy. This is without LS coupling. I am just giving you the order based on L values. L value, right? Yes. You can say in this manner also. This is without LS coupling, the arrangement of different subshells. Now, because of LS coupling, right, we get the energies of these subshell is further split into different energy states. Okay, we'll discuss that. Energy levels, right? Now listen carefully. Observe this carefully. How the 1s subshell, right, will split. Okay, because of LS coupling. LS coupling, how it will split. Listen carefully. For S subshell, L equal to 0. Remember this? For S subshell, L value is 0. For P subshell, L value is 1. For B subshell, L value is 2. For F subshell, L value is 3. G subshell, L value is 4. Like that it goes. Okay. Now, how each subshell and the energies of each level get split up. Okay, listen. To this L value, we should add S value. Only two S values we should add. One is L plus half. The other one is L minus half. Only two values we should add. Okay, this is purely quantum mechanical concept. I am just giving you the final result. Right? LS coupling split each level into two. Split each level into two. What are the two levels we get? One is L plus half level, the other one is L minus half level. Remember, L plus half gives you the lower energy and L minus of will give you the higher energy. Okay, so for this level, see for 1s level, L value is 0. To this, we add plus half and we subtract. Okay, L value is 0, so 0 plus half and 0 minus half. What we get? Can anyone tell me?
Plus half minus half.
Listen, we are taking the magnitude only. Right? I'm sorry, I didn't write that. We are taking only the magnitude. Just turn off your mic. Right. So L plus half magnitude and L minus half magnitude. For 1s subshell, L value is 0. So here we will get plus half. Here we will get magnitude of minus half is plus half only. So 1s level does not split. It remains as such. Okay, 1s level does not split. It remains as such as 1s half. So after LS coupling, 1s level remains as 1s, but we put half symbol here. This half is nothing but the J value. Right here, this is nothing but the J value. Okay, right? It is the sum of L plus S and J value. What about 1P? Listen carefully. 1P will split into two levels. 1P will split into two levels. For P subshell, L value is 1. So you take L plus half and L minus half. 1 plus half, 1 minus half. What we get? So, 1P 3 by 2 has lower energy and 1P 1 by 2 has higher energy. Okay. Then what about the 1D? 1D, for D, L equal to 2. So it will split into two levels, right? What are the two levels? Can anyone tell me? For D. So we get 1D 5 by 2 has lower energy and 1D 3 by 2 has higher energy. Okay. L value is 2 for D. What about 2S? You know very well. S for S subshell, L value is 0. Therefore, S subshell never split. Okay, it remains as such. It remains as such. So 2S 1 by 2, right, remains as such. Okay, now we'll move on to 1G. 1F. Okay, 1F. This 1F will split into 2, right? How? Yes, it will split into 2. 1S will split into 2, right? For F, L value is 3. So 3 plus half will give you 7 by 2. So we get 1F 7 by 2 lower energy. Then LF 3 minus 5 by 2 as higher energy. Then this 2P will also split into 2. 2P will also split into 2 like this. Okay. 2P, P subshell, how P will split? 3 by 2, 3 by 2 and 1 by 2.
1 by 2.
Okay, take 2. Then the G will split into 2. Let me write here. The G will split into like this. Here. Yeah. Observe this carefully, very important. Right? Then, so this is 1G. For G it is 9 by 2, right? This is 1G 9 by 2. And this is 1G 7 by 2.
7 by 2.
Okay. Then 2D will split. 2D will split into 2. 2D. We draw here. 2D will give 2D. D will split into 5 by 2 and 3 by 2, right? 5 by 2 and 2D 3 by 2. S does not split. S remains as such. So S 3S 1 by 2 remains as such. Okay. So these are all the subshells, right? Or energy levels, right? We get after LS coupling. Okay. So the 5 by 2, 1 by 2, these numbers are J values, total angular momentum values. Okay. Listen. In each of these levels, right, how many nucleons we can place? Participants, observe carefully. These are all the levels we get after LS coupling. And in each level we can place some number of nucleons. I repeat, you can arrange number of protons in this. You can arrange the protons in this. You can also arrange neutrons in this. For both neutrons and the protons, these are all the allowed energy levels. Okay, now in each level, how many nucleons we can place? How many protons or how many neutrons we can place? Okay, just use this formula 2j plus 1. 2j plus 1. So in this case, j is equal to half. If j is equal to half, how many nucleons I can place here? Right? This two cancel. 1 plus 1 is 2. So this level can accommodate maximum of 2 nucleon. It may be proton or neutron, whatever it is. It occupy maximum of 2. Maximum of 2, let me write here. Maximum of 2 protons. 2 nucleons. What about in this level? Anyone? 1p 3 by 2. J value is 3 by 2. Put 3 by 2 here.
4, sir. 4 nucleons.
So this can accommodate 4. What about this? 1 by 2 means 2, right? 1 by 2 means 2. Listen carefully. Here I can place only 2, right? Up to this, see from the base, 2 plus 4, 2, 6, 6 plus 2, 8. Up to this I can place 8. Observe carefully. Up to this, from the lower level onwards, I can place maximum of 8 here. Okay, up to this 8 we can place. What about this? Up to this, right, we can place a maximum of 20. You just calculate and see. Right, here I can place, see if I have 2 into 5 by 2, I'll get 11, sorry 6, here 2, and here I can place 4, right, so I'll get 12. 12 plus 8 is 20. Up to this I can place 20. Listen carefully. The energy gap between this and the energy gap between this is very large. So this level, right, should be given separately. For 7 by 2, 2 into 7 by 2, I'll get 8. So 20 plus 8, 28. I can place a maximum of 28 here. Okay, and the maximum of 28 we can place. Then these levels are, listen, these levels are very close. So up to this level we can place a maximum of 50 nucleons, right? Then the next one, up to these we can place a maximum of 82, right? Listen carefully. 2, 8, 20, 28, 50, 82. These are all very famous numbers called magic numbers.
Magic numbers.
Yes. Numbers are called magic numbers, which gives the maximum number of nucleons that can be accommodated, okay, up to a particular shells, right? And these, if you have arranged the nucleons, right, with these numbers, right, we can say that those nuclei are generally stable, right? Number 1. These are all some rules we say, rules. Okay. How to find? Yes, how to find the I value based, using the nuclear shell model. Right? Listen. If mass number, see A is called mass number. What is A? A is mass number of an isotope. Okay. For an isotope, for a particular isotope, mass number and atomic mass are one and the same. Okay. Now, A is a mass number. Suppose if A is odd, observe carefully, mass number is odd. Right? Mass number odd means there are 2 possibilities. What are the 2 possibilities? Let me write here. What are the 2 possibilities? See, number of proton may be even, and number of neutron may be odd. Observe carefully. There are two sources. You see, this is even, this is odd. If I add the two, you will get mass number. If I add the two, one is even, another is odd. If I add, I will get odd. What is the other possibility? Proton number is odd and neutron number is even. Okay, if I add the two, I will get odd. Here also, if I add the two, I will get odd. If mass number is odd, we have two possibilities. Okay. Now, for these two possibilities, observe carefully. For the first case, I is equal to J value for the neutron we should calculate. Because proton is even number, I repeat, proton interacts with the proton. Neutron interacts with the neutron. This is the point you should keep in mind. If I have even number of protons, one proton and the other proton, they cancel each other. Okay, one proton and another proton cancel. So, if I have even number of protons, protons do not contribute in the spin. Only the odd one we should take. So, in neutron, we have odd number. Therefore, we should find out the total angular momentum of the neutron, and that gives you the value of spin quantum number I. For this one, see, neutron is odd even number. So, you should not consider neutron because neutron get paired up. They cancel. Whereas proton is odd number. Therefore, in this case, I is equal to angular momentum, right? Total angular momentum of proton we should consider. Okay. Then, number 2, second rule. Suppose if A is even, then there are 3 possibilities we are going to discuss. Okay, what are they? A. If A is even, then number of proton and number of neutron both can be even. Both can be even, right? So that this is even, this is even. If I add the two, I will get even. If proton number is even, then protons cancel each other. So, no spin we get based on proton. If neutron number is even, then neutron also cancel, right, themselves. Therefore, you never get any spin because of neutron. No spin due to proton, no spin due to neutron also. Therefore, in this case, we can say very clearly that I value is 0 in this case. Very simple. Then, we have second possibility. What is that? If A is even, then number of proton can be odd and number of neutron can also be odd. Observe carefully. Both are odd, but in this case, what you have to do is that check whether the total angular momentum of proton and total angular momentum of neutron are the two equal or not. Suppose if they are not equal, observe carefully. If total angular momentum of proton and total angular momentum of neutron, if the two are not equal, then we can find the nuclear spin quantum number or simply spin using this formula, magnitude of Jp minus Jm. What is Jp? Total angular momentum due to proton minus total angular momentum due to neutron. Okay, subtract it and take the magnitude. That magnitude will give you the value of I. Okay, then the last case is interesting. Listen, proton number is odd and neutron number also odd. But if angular momentum due to proton and angular momentum due to neutron, if they are equal, in this case, listen, you take the magnitude of Jp minus Jm and magnitude of Jp plus Jm. Observe carefully, take the two magnitude. I value will be from this number to that number. Okay, it has some range. Okay, it has this range, right, up to this. there are many possible values of I, right? Experiment will decide which I value we should take. Okay, it will give you the possible values of I, right? Take. Right. Let me start with the proton. It's a very simple case. I'm giving you some examples. See, in this case, right, mass number is an odd number, right? A is odd number, right? And how many neutrons and how many protons are there? See, number of protons equal to 1. Number of neutrons equal to 0, right? 1 minus 1 is 0. 1 minus 1 is 0. So, since there is no neutron, only the proton decides the nuclear spin. I have only one proton. Now what to do? Place this proton in the nuclear subshells. Okay. So listen carefully. I'll go to the nuclear subshell. This is the nuclear subshell. And we have arranged the energies of these levels in the increasing order. Listen. The lowest subshell, the lowest level can accommodate maximum of 2 protons. But now, for hydrogen atom, I have only one proton. So, place that one proton here. If I place the one proton here, what is the J value? What is the J value?
1 by 2.
1 by 2. So, the J value is nothing but, so I is equal to J value of the proton, because there is no neutron, J value of proton. So, J value of the proton is 1 by 2. So, I is equal to 1 by 2 for hydrogen atom nucleus. Right? We'll move on to the second example, number 2. I'll take C613. C613. So, it has, see how many protons are there? There are 6 protons, 6. How many neutrons are there? Number of neutrons? 13 minus 6. Okay, 13 minus 6, we get 7. Okay, listen, proton number is even. You know very well. If you have even number, then the spins of each proton, right, cancels themselves. So, since proton number is even, protons do not contribute in the spin of the nucleus. No, okay. Only the neutron, it is an odd number, this will contribute. Right, now what to do? Arrange the 7 neutrons in the nuclear subshells. Listen, I am going to arrange here. Okay, I have 7, right? I have 7, I am going to arrange the 7 here. How? Listen carefully, place 2 here. 2, listen, you have to pair up. Okay, so 2, let me pair up here, 2. Then here I can place 4, right? So 3, 4, 5, 6. Right? I have 7 actually, 7 neutron. So I place 2 here, 2 here, 2 here, 6 over, and remaining 1 should be placed here. Okay, for this one, what is the value of J? What is the value of J?
3 by 2.
Observe carefully here.
I'll go 1 by 2.
1 by 2. Therefore, listen. Therefore, I value for, see, proton is even number, so you should not consider. Only neutron is odd, so I value equal to total angular momentum of neutron. Okay, and we got the answer as 1 by 2 for this 7 neutrons. Okay, the 7 neutrons are arranged and the 7th neutron actually contribute. Right? 6 neutrons, listen, first 6 neutrons, they pair up, so they cancel, their spins cancel. Only the 7th neutron, which is an odd number, that contribute to the spin of the nucleus. Okay, and the nucleus spin quantum number is half. Right? Take 2. Now, I'll give you one example. See, lithium 3, mass number 7. Yes, try this one. Yes, for lithium 7, your answer is correct. I is equal to 3 by 2. Good. Now, I'll give one more example. You try this. B511. Yes, try this one. You calculate number of protons. How many protons are there? There are 5 protons. How many neutrons are there? 11 minus 5, 6 neutrons. Since it is a even number, neutrons do not contribute. Therefore, I value is equal to total angular momentum of protons. Simple.
Proton.
So, I have 5 proton. Arrange the 5 protons in the subshells. See, I have subshell here. Arrange the 5 protons. So, 2 here. Okay, let's get paired up. Then 3, 4, 5. 3 and 4 get paired up. Fifth one is odd one. So for the odd one, I value is j value is 3 by 2. Therefore, I is equal to 3 by 2. So I is equal to 3 by 2 for B11. Like this. Listen, B5 10. Yes, try this one. Listen. So number of proton is 5, which is an odd number. Proton, okay. Visibility. Then number of neutron 10 minus 5. It is also odd number. 10 minus 5 is 5. 5 is also odd number. Right? So in this case, what we should do? We should arrange the, since both are equal, we should get JP and JN are equal, right? As equal. Okay, since both the numbers are same, so total angular momentum due to proton, total angular momentum due to neutron comes out as equal, right? If JP and JN are equal, I have given a formula for you. If JP and JP are equal, then there is a range. Okay, so what we should do? What is the JP value and JN value for 5 protons? So 2, 4, 1 is 3 by 2. So what we should do? Listen, 3 by 2 minus 3 by 2, 3 by 2 plus 3 by 2 is 3. So the value goes from, this is 0, I value goes from 0 to 3. Okay, so I can take any value from 0 to 3, and experimentally it was found that I value equal to 3 for B10. Okay. For deuterium, the possible I values are 0 or 1, but experimentally it was found that I value for deuterium is 1. It's not 0. Okay, take